Now we start with the Lyapunov stability analysis. In this we will study introduction to Lyapunov stability analysis, Lyapunov stability in sense of Lyapunov, concept of Lyapunov function and example. Now about the introduction to Lyapunov stability analysis. This Lyapunov stability analysis had been developed in 1892 by a scientist named A.M. Lyapunov, and because of his name this criteria has been called as Lyapunov stability analysis, and this work he has published in his doctoral thesis, that is in 1892. So, Alexander Mikhailovich Lyapunov, that is A.M. Lyapunov, doctoral thesis on general problem of the stability motion in 1892. Now, what is the concept? It is based on the concept of energy. If the total energy of the system is dissipated, then the system is always stable. This Lyapunov method is useful for determining the stability of nonlinear system. Now, another point, it is also applicable to stability testing of linear systems. In this approach, stability of the system is determined without solving the differential equation. This method is called as direct method. So, we have seen some points. The main important thing is that this Lyapunov stability is based on the concept of energy, and it is applicable for both linear as well as nonlinear system. Now, here the most important thing is that if you see the literature, there are many criteria have been developed or are available in the literature for stability of a linear system, but as far as the nonlinear system is concerned, there are very limited criteria, and this Lyapunov is basically useful for checking the stability of such a nonlinear system. Now, just we see what is the concept of this energy. Suppose I have some money, or the government has given a salary in the first say first day of the month. So, some salary I have got, and what has happened till last date of this month, in that month my salary has been increased. So, what do you say? We have salary in the first day of month which is high, but in on the last date of that particular month salary has been increased. So, we will say that this is not possible. That means whatever we have salary, as time progresses that must decrease. If it is not decreasing, that means there is something problem. Another example is, we can say, suppose we are driving a vehicle, it may be, and in that case what fuel we are using? We are using as a diesel or a petrol. So, we have started driving a vehicle, and what has happened? After a certain time interval, you check the petrol or diesel, that has been increased. Then what do you say? How can it possible? So, that means that is not a correct phenomena. So, what Lyapunov say that whatever the energy is there, as time progresses, that energy must decrease. So, if the energy decrease, then in that case the system is stable. If it is not decrease, it means that system is not stable. So, that is the concept of the Lyapunov. So, this is a very important concept which is given by the Lyapunov. Then the question has become how it can be useful in checking the stability of a nonlinear system. See here, whatever the system is there, the system is made of different functions. Out of these functions, some are very important, some are not important. So, what we are thinking, if you take the specific function and that particular function, if you check the stability, then if it is follow the concept of energy, then we can say that your system is stable. Let us say we take another example. Suppose a project has been given to two students, and they have started doing work, but suddenly one day it is found that the students are saying that it is not possible to adjust with that particular students. Then what I will do? I will identify the problem. What is the problem in that? But in that case I found that particularly when the part has been come for studying or developing some algorithm, both have same opinion. So what I will do, I will say that okay, you be there only for that work and don't meet afterwards. That means that particular function we assume, and I am checking and we have to check the stability around that function. So what will happen around that particular function, if the system behavior like just like energy is there, it decreases, then we can say that your system is stable. Now we see one practical example. Now we take one spring mass damper system example. We have already seen that example earlier. So we have spring and this is a damper and here is a mass, this is M and its force applied, this is K, this is B, and let us say displacement y of t and force F is applied. So last time we have seen how to determine the equation of motion for such a type of system. So now I am again writing this equation. So F equal to M t square y of t divided by dt square plus k function of y of t plus b ddt of y of t. So y is the displacement. Now we have to assume the state variable. Suppose we have taken as x1 equal to y. Now what is x1 dot? X1 dot equal to y dot equal to x2. Then x1 double dot equal to y double dot equal to x2 dot. So x2 dot equal to y dot and y dot is like here, shown here. Now we can represent the equation in this way: F equal to m this d square dt square of y of t, that is x2 dot plus k into x1, this is x1 plus this is y dot, that is equal to x2. Now suppose if you take m equal to 1, so your equation become F equal to x2 dot plus kx1 plus bx2. Suppose system is autonomous, so let us say F equals to 0, unforced system. So now the equation we can written as x2 dot equal to minus kx1 minus bx2, and here original equation x1 dot equal to x2. Now this equation has been formatted, applied force is 0, m is 1. Now the total energy of the system consists of the kinetic energy of moving mass and potential energy of the spring. Therefore here we are writing down one function which is with respect to kinetic energy as well as potential energy. So how do you write down? Now we can write down as v of function of x1 x2 equal to 1 by 2 mv square plus 1 by 2 k x1 square, this is m for mass, k is for spring. Now this equation can be written as 1 by 2 m x2 square 1 by 2 k x1 square. Now here what we are doing, we are assuming m equals to 1, so we have written m equal to 1. So above equation can be written as 1 by 2 x2 square plus 1 by 2 k x1 square. Now here v of x equal to 0 for x equals to 0, and this v of x is greater than 0 when x is not equals to 0. Now we will calculate or we will determine the rate of change of energy. So it can be written as the rate of change of energy is given by it is given as differentiation of t v x1 x2 equal to del v by del x1 into dx1 of dt plus del v by del x2 multiplied by dx2 by dt. Now this equation we have written, we have got del v by del x1. So v function we have already taken here, and what about dx1 by dt and dx2 by dt? So dx1 by dt equals to x1 dot and dx2 by dt equals to x2 dot. So we have already values of x1 dot, x2 dot. So we replace the values of x1 dot, x2 dot in this equation, and this del v by del x1 and del v by del x2 we calculate from this. So finally we can get the equation as, so del v by del x1 we will get it as k x1 x2 plus del v by del x2 equal to x2 minus k x1 minus bx2. Now after solving, what will get? K x1 x2 minus k x1 x2 minus b x2 square. So this will cancelled. So finally we got b x2 square. So if you have function and if you differentiate this function, if it decreases, it means that your energy is decreasing. What I am saying, if you have function, if you define and we take rate of change of it, if it decreases, that means that your energy decreases. So here we will find that for this spring mass damper system, we have taken a function, we have differentiated it, and we will find that this always negative for when x2 is non-zero. So here we will find that this system is a stable system. Now we have to see some definitions, that is Lyapunov stability, that is in sense of Lyapunov. As we have seen the different definition of stability, that is when input is bounded, output is bounded, then when that is called stable. Then if your roots or eigenvalue on the left hand side, system is stable, right hand side unstable. So here there are some definitions with respect to Lyapunov. So we will see what are the definitions. Consider the system as this x1 dot equal to a of xt. This is a unforced system. Here there is no u, input is 0. So this system is stable at origin if for every initial state x of t0 there are some initial state which is near to origin. Origin is the equilibrium point. Let us say state which is near to origin, this x of t remains near the origin for all t. That is when the system is stable. Second, system is asymptotically stable if x of t approaches the origin as t tending to infinity. What happened? We have say origin, now initial state. So earlier what happened? The state started at it will remain near to origin, but now at t tending to infinity, whatever state started, it will approaches towards the origin, that is asymptotically stable. Now another point is that asymptotically stable in the large, how do you define it? So if you take different initial state, for every initial state the trajectory or state will move towards the origin, then we can say that it is asymptotically stable in large. That means for whatever be the initial state, for every initial state system is approaching towards the origin or trajectory approaches towards the origin, we can say that system is asymptotically stable at large. Now we will see this definition in different aspect. Now we take one region, this small region, and we take another regions, and what we want that this particular region is the stable region, that means whatever trajectory should remain in that region, and these small regions which is defined as S of small r, and here is this r, and then this is the origin, this is the equilibrium point. Now we take one trajectory, let us say which is nearer to origin, which is nearer. Now it start moving, so when it start moving, it will moving and it will not coming back, but it will remain here. That means here is system is only stable, Now we take another region, so the initial inner region, outer region we have determined. Now here again this is r, the origin is S of r, here S of small r. Now here a trajectory again which is near to origin, and it will start moving, and finally at t tending to infinity it is approaches toward origins. Here it is approaches like this. If this is the condition, this is called asymptotically stable system. Now you take same regions, inner regions, and now here is the outer regions. Again this is radius r, this is region S of r. Now here is a small region S of r, small r, and now here is the origin. Now again the trajectory. Now trajectory which is near to ring, starting from here, it is not coming back, and now it is moving outward. So this is known as unstable. This is unstable. This is only stable, and this is asymptotically stable. Again, if you find that here, if you take this initial condition for different initial condition here, if the trajectory again moving towards the origin, then it is called asymptotically stable at large. So we will see it here. Lyapunov stability is defined about the equilibrium state which is located at the origin and x of 0 equals 0. Let SR be the spherical region of radius r greater than 0 around the origin, where S of r consists of point x satisfying norm of x less than r. So this is the case. See here, this is the case, and this origin is said to be stable in the sense of Lyapunov, or simply stable if corresponding to each S of r there is S small r such that solution starting in S of r do not leave S of r. So we will find that here the solution started from here, it will remain in the region, it is not going outside. So that is why this we call as the system is a stable system. And then asymptotic stability, if the origin is stable, and in addition every solution starting in S of r not only stays within S of r but also approaches the origin as t tends to infinity. That means that what are the initial state, it always approaches to the origin, then we call as it is asymptotically stable system. Now we start solving some example based on this concept. As we seen that this Lyapunov stability is basically applicable for both linear as well as some non-linear system. Now first of all we see the stability testing for a non-linear system. So here we are taking an example, say x1 dot equal to x2 and x2 dot equal to minus 2x1 minus x2 whole cube. Now this is the state space model which is in non-linear form. Now we have to check the stability of the system. Now how to check it? As I told you that, so nonlinearity means that nonlinearity means for any system, nonlinearity just it's not like that for it to remain everywhere. So for small parts system may be linear. Therefore what we are doing, we have to assume some function. Now here basically function which we have to assume, that must be positive definite function. That is why last time we have seen the how to check the definiteness. So here our main purpose is to assume a positive definite function. So you will find that earlier also this particular function, this is also a positive definite function, that is for all x1 and x2 not equals to 0, this v of x1 x2 always greater than 0 except at equilibrium point when x1 equal to 0 or x2 equal to 0. So here we have to assume a Lyapunov function. So which is the Lyapunov function we assume? So the best Lyapunov function we assume, that is we can assume v of x equal to x1 square plus x2 square. So we will find that if you x1 and x2 greater than 0, v of x is always greater than 0. So that is a positive definite function, which is very simple one. Therefore when we solve the example, generally we assume this particular function. So here taken v of x equals to x1 square plus x2 square. Now we have to check the stability of the system. So here what we will take, what we will do, v dot x equal to del v of del x1 multiplied by dx1 dt plus del v by del x2 multiplied by dx2 by dt, because we have we have discussed earlier, we have to take a function. It is, if you take the derivative of the function, if it decreases, means that energy decreases. That is why here we have also done the same thing. We have taken v dot x and we have to see that whether that v dot x is negative or not, or in other words we have to see that whether v dot x is negative definite or not. So here we have written the equations. Now we replace the values of del v by del x1, del x1 by dt, del v by del x2, also dx2 by dt. So here what is the value of del v by del x1? So del v by del x1, if you see here this equation, so what will get? You will get 2x1 multiply dx1 by dt, that is x1 dot, and that is equal to x2, plus del v by del x2, del v by del x2. So here with respect to x2, so what will get? We will get 2x2 and del x2 by dt, that means x2 dot, you will get it as minus 2x1 minus x2 whole cube. Now we solve it. So what will get? 2 x1 x2, here 2 into 2 is 4, minus 4 x1 x2, and here minus 2 x2 raised to 4, and now here if you solve it, you will get it as 2 x1 x2 minus 2 x2 raised to 4. So we got v dot x. Now here you see, you take any values of x1 x2, but which must be greater than 0. That means if you take this x1 x2, x1 x2 greater than 0, for any of these values of x1 x2 which is greater than 0, you will get v dot x is always less than 0, except one condition, when x1 equals 0 or x2 equals 0. So if this is the case, it means that v dot x is negative definite, less than 0. It means that our system which we have considered, this is a stable system, this is stable, this is stable system. But here this is the issue, because here we have taken one specific function. So it may possible that if you take a different function, it may possible that this system is unstable, maybe it may come unstable. Suppose what I am saying, that instead of this function we have taken some different function. Let us say we have taken this function as 2x1 square plus 4x2 square. This is also a positive different function. If you take it by chance, after taking this one, if you got v dot x, let us say greater than 0, then you say that system is unstable. It means that here for v of x we could get the stable, for v dot x for this particular function we have got unstable system. It means that this particular Lyapunov criteria is only giving the sufficient condition for stability of the system. That means stability is concerned with the function only. That means if the system is stable, that particular function only, and if the system is found to be unstable, we cannot say the system is unstable. It is unstable only for that function only. So this is the one important point regarding the stability of the system, stability of a nonlinear system using the Lyapunov method. And the most important point that the Lyapunov approach is only giving the sufficient condition of stability of the system, and mainly it based on particular function. For the particular function, if the system is stable, then we can say that the system is stable with respect to Lyapunov for that particular function only. Now we take another example. Let us say x1 dot equal to x2, x2 dot equal to minus 6x1 minus 5x2. Then we take Lyapunov function as a simple function. We can take it as v of x equal to x1 square plus x2 square. Then we can take v dot x equal to, again same, del v by del x1 dx1 by dt plus del v by del x2 dx2 by dt. Okay. Now we have to solve it. Same here, del v by del x1, that is here, and del v by del x2 is here. So after solving it, you will get 2x1, here we get x1 dot, that is x2 plus 2x2 multiplied by x2 dot, that is minus 6x1 minus 5x2, and here after solving you will get 2x1 x2 minus x1 x2, here minus 10 x2 square, and again here you will get it as minus 10 x1 x2 minus 10 x2 square. So again you will find that you can take any values of x1 and x2 or any positive values of x1 and x2, you will find that v dot x is always less than 0. That is, if you take x1 x2 greater than 0, so this v dot x is always less than 0, and we say that this is also a stable system, and you will find that in this particular case there is no need to calculate the eigenvalues, only we have to take the function and differentiate it, you can get the stability of the system, and this is very much important criteria. Even though this criteria is very old, say around 130 years back it has been developed, but you find that in the literature on particular research domain still this criteria has been widely used in application. So this is a very important criteria. Now there are some references: IIT Nagraj, M. Gopal, Control System Engineering, 5th edition 2007, D. Roy Chaudhary, Modern Control Engineering, Print Press of Hall, India, 2005. Thank you.